Recording. Okay. You don't mind that I record, right?
Sure.
Okay.
All right. Thank you, George. Thank you for the presentation and for introducing me. Today, I'm going to talk a bit of my work, of the work I have developed in my master's in collaboration with George Martins, our dear host, and also with Luiz da Silva, who's also here with us. Our work is mainly focused on study the magnetic fluctuation scenario of the Moiré superlattices, with taking as a specific case study of twisted bilayer graphene. Here we're still more interested in how the long-range interactions influence this kind of system. As I will show you, they are relevant in these so-called Moiré patterns. So this presentation is structured in the following way. I'll introduce you to the Moiré patterns, showing how how there are its lattice structure, the different stacking patterns, and how the twist angle can emerge different and interesting physics to several layered systems. I'll then start discussing the specific case of twisted bilayer graphene and how these correlated states they have been observed experimentally. Then I will move to a more theoretical perspective on how to study magnetic fluctuations. I'll try to connect the quantity, the susceptibility quantity to an experiment, the neutron scattering experiment, to give you some intuition on how magnetism can be probed by this quantity. And then I will connect that to the picture of Fermi surface nesting, trying to explain to you what's that and which kind of physics we can observe from it. Finally, I will present to you the perspective of what is a RPA approximation and how it is connected to a concept called the Stoner criteria. Finally, under the RPA approximation, I will show you how some results for this calculation of superconducting gap, and start to then apply all this theory to the twisted bilayer graphene system, where I would like to discuss with you some possible non-interacting models and also some results for the superconducting ground state phase space for this material. So first of all, what's a Moiré pattern? Well, we start with two sheets of, for example, graphene. Graphene has an hexagonal lattice, and then we align these two sheets and we rotate them, we twist them by a certain angle theta. For example, the one point which is not rotated is, for example, this point here labeled A in the middle of the picture, where there are two carbons overlapping. This one spot is called an AA spot, but it is not the only one in this present when you do this twist. There are also two other kinds of spots, which we call BA and AB. The BA spot has a carbon centered in the bottom layer and the center of an hexagon in the top layer. And the opposite happens in the AB spot. So in practice, when we do this twist, we obtain a system which has an hexagonal lattice unit cell. So the lattice now can be described by symmetries of a triangular lattices plus these two elements in the basis for the BA and AB sides. And that happens for the Moiré patterns. But that can actually generate some very interesting scenario by the following way. As we can actually estimate that the length scale, the new unit cell lattice parameter, is inversely proportional to the sine of the angle, the twist angle, in such a way that if this angle is small, so the new lattice parameter is really big, the new unit cell have more and more carbon atoms inside of it. So for example, for these smaller angles in the bottom here I'm pointing D, the unit cell, it has around 10 nanometers, and then as you increase the number of the twist angle, this unit cell decreases, and you can start to recognize some carbon atoms, because otherwise you can distinguish them of so many that they are. And we can actually observe that experimentally. So I show here some STM experiments for a small angle, for example, 0.1 degree. This unit cell is of around 100 nanometer, which is huge. So as you increase the angle, it becomes smaller and smaller, as you can see by these insets. We see this pattern now being reproduced in smaller scales. So that's the scenario of the Moiré pattern. The lattice parameter highly increases at small angles, and that can actually make really interesting physics, because now the as the lattice parameter increases, the lattice parameter in the momentum space, meaning the momentum space Brillouin zone, now decreases of size, meaning that momentum values of the systems are smaller. And that can actually make these scattering events between small values of momentum more and more favorable. But scattering events of small values of momentum mean actually long range in real space. So this kind of pattern can actually favor long range interactions in real space. But besides that, we can also see another very interesting phenomenon happening, which are the so-called magic angles, where this kind of twist in these Moiré systems, they can generate something called the flat bands, which can be observed actually experimentally, and have been by direct measurement, like here in ARPIS, this 2021 paper. It's a beautiful paper because, as I just said, the momentum space, the momentum Brillouin zone is really small. So you do need a very good definition, a momentum definition, and energy definition to get this kind of map. So these are really special experimental works. And there are several interesting phenomena happening in these kind of systems. For example, talking about magnetic order, we can observe nematicity, as in this paper, this plot here, they are showing X direction and Y direction field, and in colors, the resistivity measured for a given region of the sample. And what we can observe is that these maps, they present some anisotropy, which is a clear sign of nematicity in the system. Also, we can see we can also observe different charge order, like in this also STM experiments here that could probe charge charge densities in twisted bilayer graphene. This kind of phenomenon mainly happens for lower temperatures. So it is a really rich system, but we don't have to stop there. Well, 2 layers are really interesting, but why not more? So an immediate step on literature can go through is increasing the number of layers, and it has been done. For example, this year the science paper has studied how this few layers of ABC stacking graphene can generate these flat bands and actually present superconductivity in it. So that's the whole scenario of a part of the scenario of this graphene layers, few layers systems, and there are also the now emergent the called TMDs, transition metal decalcogenides. But now let's move a bit to from the theoretical point of view, how we can probe magnetic fluctuations. So I'll start talking about an experiment, a neutron scattering experiment. So consider a linear chain of pure magnetic sites. So if they are, as they are ferromagnetic, all the spins are aligned. For example, suppose they are all up. There is a lattice parameter A, and we can then define this quantity called rho, which is the projection of these spins over the x-axis. We take then rho square, and that's basically as probability density for this projection. In principle, without any further perturbation, this rho square will present something proportional to a cosine of 2 pi over a times x. And now what we're interested in doing is actually present a perturbation over these spins. So we start shooting neutrons over this chain with initial energy E and momentum K, and final energy E prime and momentum K prime. After the interaction, this as we're talking about neutrons, they have no charge, so they only interact with spin. After the interaction, they will probably flip their spin and have as consequence present a perturbation, make a perturbation on the heated lattice site. As this site is perturbed, its neighbors will also tend to, now as this is a ferromagnet, the neighbors will tend to align with this spin also, but in phase, because they want to totally align with it. So now, in terms of equilibrium, the whole chain will be rotating or under this perturbation in phase. And in average, then, this function rho squared won't change at all. But what does it mean for an experiment? Well, in an experiment, we measured how many neutrons with certain energy E prime and momentum K prime are getting to the detector. And the quantity of neutrons measured for this given pair is the susceptibility. Is the susceptibility quantity. So in this kind of a histogram, as we increase the number of neutrons measured, there will be some certain values of momentum difference Q equals to K prime minus K, and energy frequency E prime difference E prime minus E, that will be more pronounced, more often measured. And in this case, it will be Q equals to 0 because there is no transfer of momentum between the neutron and the lattice. But that scenario is not the same as it happens in an anti-ferromagnet, because now the spins are anti-aligned, and once this first perturbation is done, the spins now tend to anti-align with the perturbed one, making them all start to also rotate, but out of phase. So if one rotates to anti-clockwise, the other one will be clockwise, and so on, so forth. And but now this will actually introduce a new pattern for our projection density, which will now present peaks where it was not present before. This means that the new projection density has now a certain phase, a new momentum value, a wave vector which is being induced in the chain, and it is being induced because it's being transferred from the neutron to the chain, and that's measurable by the susceptibility experiment. Here, the wavelength is of 2a, so the momentum, the scattered momentum, I'm introducing this notation, which is the Q value, K prime minus K, will present a peak at pi over a. So for an anti-ferromagnet, the peak is at pi over a, because that's the momentum transferred for the chain from the neutron. But for a ferromagnet, it's Q equals to 0. And that's how to probe magnetism from the susceptibility measurements. Okay, so I expect that's a bit more clear. And I'm trying now to connect this scenario with another interesting quantity, an interesting phenomenon, which is the phenomenon of Fermi surface nesting. So let's take another practical example. Consider a square lattice. It can be shown that the susceptibility, the same susceptibility non-interacting quantity can be expressed by this kind of summation here, which I will make it clearer in a moment. So first of all, consider the Fermi surface of it. At zero doping, at half filling, the square lattice has a tilted square as its Fermi surface. And what we can observe here is the following. From this expression here, see that there are two energy differences in the denominator. And we are interested in the Fermi surface, meaning that this omega value, the E prime minus E, is 0 for this Fermi surface events, scattering events. So as the energy calculated at K plus this certain scattering vector Q minus E at that same momentum value is 0, as its difference is 0, this quantity will increase, causing a peak. So for example, for this surface here, there's this whole surface on the Brillouin zone that can be translated by this vector Q equals to pi over a to this other region here. And they match exactly. So this vector Q will for sure result in a peak in this quantity. Now I'll go a bit further on the meaning of this expression here. Well, for each pair of momentum and taking a frequency omega equals to 0, we can obtain 1 point in this kind of diagram. So the moment we are talking about a 2D system, so there is a Q, X, and QY components. In colors, there is the susceptibility values. And what we are calculating here is that for each one of QX, QY pair, there is one scattering event of this type, where there is this recurrence of K plus Q momentum for each electron scattering. And then a momentum Q is propagated. So that's the picture for each pair QX, QY, one momentum, one scattering event. So here, what we observe is in these yellow regions of this map, there are the greater values of momentum, of susceptibility, meaning that these events are more probable to happen. They happen more often. And they are exactly at pi, as we just deduced it, as we were expecting. So there is a peak here because there's this vector Q connecting the Fermi surface region to another one. Not one point, but a region of it, where you can integrate over it. So that's called Fermi surface nesting. And this Q equals to pi is the nesting vector. Okay. Now I'm trying to move a bit for to how to model twisted bilayer graphene, and then we will introduce interactions in our theory. So let's try to not keep theoretical all the time and go to this specific case study. So now we come back to twisted bilayer graphene, where there is this rotate angle, and we are interested in a non-interacting model for it because it has, as I just showed, the Fermi surface is a very important property of the system that we should have in order to calculate susceptibility and to have the nesting vector and everything going through these kind of calculations. So we do need good models. Although I'm going to talk to you about twisted bilayer graphene, this idea of going after good models that reproduce well Fermi surfaces is a general thing in the RPA studies. They depend on Fermi surfaces. So it is useful to keep in mind that the procedures that I'm going to show you, they can be taken and used to other systems too that you're studying under RPA. So the first thing we have to see here is, well, we're talking about a very specific structure, the Moiré pattern of twisted bilayer graphene, and well, there should be some at least some laws that should say to us that not anything can be done with this kind of system. And actually there are some symmetric properties that have to be obeyed. And this 2018 paper has shown that. So any model that we choose for reproduce the Fermi surface and the non-interacting states of the system they should obey to these symmetries, constraints. But it's not just that. We also have to look to experiment. And actually in experiment, what we see is that if we do our measurements at hole doping or at electron doping, actually the phase space, they're not quite the same. So there shall be, it has to be electron hole symmetry breaking in this model, and basically that's what it is observed in the band structure of twisted bilayer graphene. Okay, another. So some works have worked on this kind of models, trying to make it accessible for calculations through mapping it to time-binding models. For example, this 2018 work, it has developed a continuum model and then mapped it into a time-binding model that becomes better and better in agreement with the continuum model as you increase the number of neighbors considered in this mapping calculation. But not only this so-called continuum model, which has some approximations, has been proposed, also an atomistic modeling has been proposed in 2018, and also a time-binding model was tried to be fitted from it. Although it converges slowly, the atomistic model has some nice advantages for the non-interacting structure, since it introduced less approximations. Still, this first model from the continuum one is more, it converges faster, so it is less computationally expensive, and at the same time it also obeys the symmetries. Most of the symmetries the literature has reported that they are important for this kind of system, for twisted bilayer graphene. So basically, this is what we're going to use, and even being less expensive in real space, though, there are more than 1,000 lines of parameters of hopping parameters to be Fourier transformed to momentum space. So it's still quite computationally expensive for large-scale simulations. Well, next we're moving through to the interacting scenario. So what I would like to point out here is we can do that same mapping of susceptibility by Qx and Qy momentum values, scattering momentum values Q. But in this case, it is hard to distinguish at first view where there will be a peak or not. And that's because the non-interaction susceptibility is not enough to assert that a certain combination of Qx, Qy momentum, or a certain, in this case, a certain scattering event will generate magnetic order. I mean, you cannot be sure that this is a nesting vector or this other point is a nesting vector for the system. You have to turn on interactions. Once you do that, then you can say, okay, so now I'm sure that this point actually produces a peak at the susceptibility measure and susceptibility quantity, and okay, this is a nesting vector. This is generating magnetic order. And now we move to it. Well, to add interactions, we have to do the following procedure. we start with a general Hamiltonian 8, and we separate it into a time-binding model or an interacting Hamiltonian, typically a time-binding model, and an interacting part, which will split into charge and spin parts. Once we do that, we can compute the RPR susceptibilities, which have this shape. And part that I would like to point out here is the validity of this approximation. So basically, in this kind of calculations, we neglect higher order diagrams and we stop perturbation expansion up to first order. So this expression here, it is valid up to a certain value, up to this denominator here to become 0. Because as it happens, this value just goes to infinity, and all beyond that is cannot be trusted anymore. So the criteria for that is that this US and UC interaction matrices should be related to the non-interacting susceptibility, the BR1 that I just presented you by these relations, and these are called this Toner criteria, establishing the limit of validity of RPA. Okay, all set up. We know our limitations. Now we have to propose a model for the interacting Hamiltonian. And although it seems a huge equation, a lot of terms, there's a lot happening here, I'll try to go through it step by step. So the first element is a Hubbard type. So it's on site, you need opposite spins occupying the same orbital for this kind of term. This U prime term, it controls interorbital interactions. The first J is exchange interactions, the one of usual quantum mechanics, introductory quantum mechanics courses. While this J prime is similar to J, but J in the shape of J prime, they are a bit more general. But if you're talking about just one electron with one electron interactions, J prime is just J over Q. And the other terms, these U's, U primes with with indexes, and also subscripts, and J prime with subscripts, they are the long-range interactions, and they are given by this kind of diagram here. For the twisted bilayer graphene, you do have U for on-site, U1 for the first neighbors, U2 for the third neighbors, and there are all these blue squares, third, fourth, fifth, and so on. Here show up to fifth because these are the maximum long-range interactions we are going to take in our work. They can be calculated in a quite straightforward way once you do have the Vanier orbitals in your system. So the only thing I would like to note here is this first term, those are the Hubbard terms and then the exchange terms, but they do present a dependence on one parameter, which is the one free parameter, which is this relative permittivity, epsilon. And now this parameter is really interesting because it is substrate dependent. For example, for this peroxide substrates, they are around 3, but for other substrates, they can vary a lot. They can be, some recent works have also shown that they can suffer some kind of screening, So they can be either smaller or greater depending on the substrate and and of the environment of your system, of your given system. So actually this quantity is tunable and still more in these layer systems where we can really well control the environment. So now we do have interactions strengths that are tunable. Okay, so let's take a look on how this theory applied to that susceptibility calculations I have showed to you have a consequence to it. So suppose there is a control parameter V naught, just establishing the amplitude, the general amplitude of all these long-range interactions. And here I'm showing you interactions up to 50 neighbors according to the same continuum model calculated by Cochino in this 2018 paper. So first we start with non-interactions, any interactions at all. And then these two maps are the same, exactly the same, as one can actually prove rigorously that they are always the same when interactions are null. But now we start to add interactions a bit. And as we do that more and more, we see that there are some peaks being pronounced. And what we observe in general is there are peaks for both charge susceptibility and spin susceptibility. So all this region around the zero, the Q equals to 0 of scattering momentum, and these 2 points here in these two kind of events of QX, QY pairs, they are being pronounced, meaning that there is order being generated as you increase in the systems, in twisted bilayer graphene, and both spin and charge order. We see that spin is, for example, allowing we to observe pneumaticity, as charge also is in agreement, qualitative agreement with experiment, as we see charge order in twisted bilayer graphene. And the argument here is this happens, charge order happens because there are long-range interactions. Because in other systems, like in the iron pnictides, which are basically the most success of the RPA theory, there is only spin spin order, because there is also only on-site interactions. So this long range is now favoring charge order. Now we move to also connect this magnetic scenario with the superconducting scenario. And we do that in the following way. Well, we define a certain momentum-dependent gap, which is given by a certain amplitude and a phase, a k-dependent phase G. And all the symmetries of the gap should be inside this phase, of course, because the other term is just an amplitude. Now we can kind of redefine that in a more interesting way for our studies, normalizing it and normalizing this amplitude up to 1. But now this parameter lambda will be connected to our previous study. because as lambda is greater than 1, and in our calculations, lambda can be greater than 1, but as this happens, it is not superconductivity anymore. There's something else happening. And actually, that's a consequence of the Stonic criteria being achieved, meaning a transition between a superconducting state and now another magnetic state, possibly being generated by spin or charge order, the one that diverges faster. Remember that denominator controlled by this parameter? Yes. So that's causing suppression of superconductivity. So let's apply that for a certain system before moving on. Take our square lattice. It has been our friend so far in this presentation, and we plot this lambda parameter, which is called usually called the pairing strength, up between values of 0 to 1, and we change the Hubbard U up to a certain extent where this lambda parameter achieves 1. And what we observe, what I show here is in blue, the leading gap parameter and the subleading one. And what I show in this other figure here is the gap function. I mean, this function here containing all the symmetries, the gap, the momentum-dependent gap structure for the Fermi surface of the system in colors. So it takes positive values in certain regions and negative values in these other ones, meaning asymmetry, which is now as D-wave superconductivity. And actually, that's really interesting because in the most famous systems present in superconductivity in a square lattice, the cuprates, so-called cuprates, they do show D-wave superconductivity, and we can measure them. So that's the whole picture we can analyze using this theory. So let's now move to twisted bilayer graphene. Okay, let's try to model the long-range interactions in the following way. We still take that same huge Hamiltonian, but here there's a simpler picture for you to try to follow. So we take this. Here I represent the fractions between the long-range interactions sites. So this first one, U1 is the first neighbors, and here it is represented by a factor of 2, and the second neighbors by a factor of 1, third neighbors factor 1, and the fourth and fifth, they are taken as 0 in this first model. And also all exchange interactions, they are set to 0 here for this first analysis. So basically, the first neighbors interactions are twice twice the second and third ones. And performing these simulations, we see the following. First, I would like you to recall that if lambda is greater than 1, superconductivity is suppressed. So here I show these maps of U1, the first neighbors interactions parameter, and U, the Hubbard one in the x-axis. And in colors, I'll show you the lambda parameter, this one, the interaction strength, which is 0 to 1 in the superconducting state and greater than 1 when superconductivity is suppressed. So all this blue region up to the white one is superconductivity, and all the red region is certain magnetic state that is suppressing superconductivity. So as we have seen, this magnetic state can be either either caused by spin or charge in our twisted bilayer system. And now what I would like to point out is this progression under types of quantity of doping. So in twisted bilayer graphene, we do have up to 8 electrons per site in an effective modeling, and what I'm taking here are only whole doping chemical parameters, chemical potentials. So for this first case here, for this n closer to the zero energy, the half filling, which will be 4, n equals to 4, it is placed exactly at a Van Hoff singularity, and at this value, with this Fermi surface, what we observe is a continuous suppression of the superconducting state as you increase the long-range interactions. That's one trend. But as you move to another kind of Fermi surface in this band structure, which are this called in a funny way called fidget spinning in the literature, we actually do see something really interesting, because now as you increase the long-range interactions up to a certain extent, you also favor superconductivity, allowing greater values of U parameters to hold in the system. And I would like to point out that actually that's something expected from the system, because we can actually expand the interaction diagrams for this system containing long-range interactions, and what we see is there are terms that are attractive and others that are repulsive when you have long range. And what we are observing here in these maps is the attractive terms, they are leading ones up to a certain value of critical value of U1 parameter, which will be the long range strength, interaction strength. But after that, the repulsive ones, they dominate, and then they suppress superconductivity. And that also happens for still other values of doping, but now for smaller values of interactions, of long-range interaction strength. Yep. So that's the really interesting and rich scenario here in this modeling. But I would like to show you another way of modeling the system too. Now, okay, we understand what happens as we increase, as we change the values of long-range parameters and interactions. But what if we turn on the J parameter? I mean, the exchange between the exchange on site and also in long range. Well, it happens the following. Let's take this model here, which was developed also by that 2018 work that I used before for modeling the susceptibility I have shown to you. That calls this charge and spin order, and they compute the fractions between these long-range interactions and neighbors. So that's now set. And what we do is changing the Hubbard parameter U that controls all these first line interactions here, and the exchange parameter J that controls all the second line. and we change that from 0 to 1, from 0 to u in this case. And what we observe is the following. Now, in the last results, there was a continued suppression or enhancement of the superconductivity in this system. But with J, it's not exactly like that. Actually, with J, there is a first order ground state transition here. So all these zero temperature calculations or close to zero temperature calculations, they have a dependence with J, which is not important at all for the fact that there is superconductivity, the blue region or not, up to a certain value of J, of fraction J over U, and then just after you achieve it, superconductivity starts to be suppressed. So that's also a very special trend that we have observed in this system. Well, now I'd like to summarize what everything I've shown to you. So I tried to argue that the Moiré patterns, because of this high increase in the real space lattice parameter, can actually favor long-range interactions because it is causing a decrease on the momentum space lattice parameter. And also, I have shown to you that these long-range interactions, they can then favor charge order, which was not clear when these other interaction terms, they were off for other kind of system. And this observation of charge order is consistent qualitatively with what's observed in experiment. Also, I've shown to you that these long-range interactions, they also can either favor superconductivity or suppress it, which is a very curious result. And as I explained, it can be understood under some diagrammatic analysis. And finally, that there is a first order ground state transition when we change the exchange parameter in the system, meaning that it is not that important parameter if it is not great enough for superconductivity. Well, finally, I would like to thank the funding agencies and thank you all for your attention. And now I'm open to questions.
Lauro, thank you very much for this very nice seminar. This is a very exciting system. You attracted a lot of large audience. So this seminar is open to questions. We don't have Edson here today. He always has questions, but feel free to ask some questions. I have Nancy is typing something. So she will get in touch with questions. Okay. Yeah, I have a couple of questions. This if you could go back a few slides. This one with J. Yeah. All these values of J are positive, right? You are only considering, is there a reason why they are all positive? Yeah. Did you?
Well, they were a physical reason. Well,
yeah.
They are a result.
Yeah, because I recall from the when I applied RPA to the iron pnictides and to the bismuth compound, J was positive too, but it was only on site. And the model I was using was only on site. And in that case, you could ascribe that to Hund's coupling. So I assume that in the case where you have on-site, you explain that as being, you can explain that as being Hund's coupling, right? And then it tends to be positive. And but is there a reason why J is positive for long range interactions?
Yeah, in general, it seems that this is how to those J's are calculated by means of these expressions. So it seems that it happens that the Venn functions, these products, they are positive in such a way that the integral is positive.
They are positive by definition.
So these overlaps, they turn out to be positive for twisted bilayer graphene.
Okay. And let me see if anyone got anything here. Okay. And if you could go back a little bit, did you manage to qualitatively, at least, where you showed the evolution of the interacting susceptibility with the interaction strength? It's here. Yeah, were you able to what feeling is that, and what is the associated Fermi surface? Did you manage to locate a nesting Fermi surface for?
Yeah, I did.
Okay.
Yep. Let's go to it. Okay, I was prepared to that question.
Okay. Yeah. So, it's always good. It's always good to have extra. Yeah. Nice. Okay.
So this is the scenario. We have basically this kind of nesting. So in green, there are the vectors for the charge susceptibility, and these purple ones, they are for spin. So here I show some possibilities on how this nesting could be happening. So you basically have to think that an entire region of the Fermi surface is being translated to another one. So the picture is basically this one. For each one of these vectors, you do this transition. So for example, for some of these vectors, there are some translations which are interbands between different bands, and others there are intra-bands, which is also super interesting too.
Okay, so you can you expect that this is coming from nesting, but that's not surprising. But it's always nice to see that the vectors that give you the peaks are associated with nesting Fermi surface. Eric has a question. Eric, you go ahead, please.
So thanks, Lauro, for this really nice talk. I mean, I have quick questions. So first, you show both the spin and charge susceptibility. So I wonder who usually wins. I mean, either you have charge or spin susceptibility. I mean, who is the more likely to win? At least the relevant parameters, and which kind of orders we have. I mean, at least this RPA predicts. We just showed the susceptibility diverging, but I would like. I didn't get the orders, the real space
Mm-hmm.
orders. Thanks.
Perfect. Thank you for your question, Eric. So the scenario is the following. What we see in by slightly increasing this control parameter V naught is that the charge susceptibility, it increases slowly. It is slower increasing regarding the as in comparison to the spin susceptibility. So this implies that when you do have that, you go to the Stoner criteria, for example, this one here, it will happens that the charge susceptibility will it will diverge first, meaning that the spin susceptibility will diverge first, meaning that it will generate order first, and therefore all the suppression of superconductivity we are seeing is most likely caused by some spin order. Okay, because spin is diverging first. So if there's charge order, it is beyond that all the transitions we have observed. I mean, there is charge order, but it is beyond, and we are not seeing that directly suppressing superconductivity. Another thing, your other question was regarding the type of orders. So what we can observe in the RP calculations is the type of orders are what we can call is either ferromagnetic or endoferromagnetic, or some theori, which is middle them in the middle of them orders. In a more precise way, this has as a consequence a spin density wave order. So basically, this chi-s is probing some a spin density wave. That's what literature has converged to lately.
And if I may, just
I'd love to know which spin wave. That's precisely the question. Which is the Q vector? Which kind of?
Yeah. What was the Q vector? So what do you expect as a real space order? Is there any observation of magnetic order in this experimental observation of magnetic order in the system? Because this would help answering the question, maybe.
There are some recent. I'm really not sure, but it's not something that is super obvious. That everyone knows that there is a interferomagnetic dome or something. It's a bit tricky.
Okay, but there is no clear pattern that you can tell, well, spin up here, spin down there, and so on and so forth in real space.
No. Yeah, I haven't thought about it. That's actually an interesting suggestion. I haven't tried to do this exercise, but basically what I could try to think about it is the following, because in twisted bilayer graphene we do have in each of these AB or BA spots there are up to 4 electrons. That's the picture people, the literature agrees about. So you can basically place a certain Venier orbital on each of these sites, and each of these Venier orbitals has a PZ-like angular momentum. So the possible values are plus or minus. So basically, you do have these 2 orbitals centered in each of these sites, AB or BA. meaning that in these two orbitals you can fit the four electrons. So it's a bit hard to establish a picture like that, side by side. Once you do have a lot of carbon atoms, maybe by this kind of modeling, by this effective modeling, but maybe by an atomistic modeling, you could go closer to a picture like this. Does it make sense?
Okay, thanks.
Because it's not, we're not considering on-site or carbon by carbon, where you have a clear picture of spins up and down. We are considering effective electrons in each of these unit cells. It's a bit.
And all your results are below half filling, right?
They are below half. Yeah.
They are I remember seeing 1.7 or something like that, where half filling is 2, right?
Half filling is 4.
Oh, half filling is 4.
Yeah, because there are
okay.
8 electrons.
There are 8 electrons because you have two sites per unit cell. Okay.
2 sites and 2 orbitals.
2 sites, 2 orbitals. Okay, 4, 8. Yeah. Okay. So you are way below half filling.
No, in this case, we're not way below. It's
3. Okay. Yeah, I need new glasses. Okay. Yeah. The other one, 1.509. Okay. Well, the one that was very interesting was the 1.5, where you saw that increasing long-range interactions, you strengthen superconductivity. You make you increase TC, let's say. Okay. Yeah, that was really a nice result. That's
not TC, but U1C or something. Here, these are ground state phase diagrams, so T equals to 0.
Yeah, but that means that the pairing is stronger, no?
Mm-hmm.
Then TC should be higher. If the pairing is stronger, then TC should be higher. But anyways, you show that you go from non-superconducting to superconducting. If you go in a vertical straight line around 1 in the middle diagram, yeah. You go from non-superconducting to superconducting when you increase long-range interactions.
Long-range, yeah.
Okay, yeah, that's very nice result. So any more questions? Luis is still there. Do you want to make any comments, Luis?
No. Yeah, we have seen some of these results, and Lauro posted some other new ones, and I think you're completely right that this reentrant behavior kind of, these kind of shapes where you have a situation where for a given U, if you increase U1, you go from into a superconducting phase. That's really interesting, and we'll be curious to see if you keep J equals 0 and you add the U3, U4, or you add the U4 and U5, and with different ratios, what if you can get something similar or maybe more pronounced. So it would be interesting.
Yeah, that would be long-range repulsion leading to pairing. That's very cute. That's very cute.
That's what's happening actually, and this happens for a very specific reason, because this 2020 work, it has showed some diagrams for the long range interactions, and what they show is actually there are some terms for this interaction pairing strength, pairing vertex, which are positive or repulsive, but others there are negative or attractive. And what we're showing is that these terms here, they can lead, they can be more important than the repulsive ones for some values of U1.
Sorry, I just want to point out, this is not from the 6, it's just convoluting theory. The problem is TC is just too low. I mean, you may try to calculate TC. Usually comes down to like 10 to the minus 6 from the Fermi energy. It's just too low. And the mechanism is convoluted. It's just RKKY. I mean, because the oscillations you can get pairing, and you need long range. It's convoluting. This is from the 60s. This 2020 paper is nice. I mean, they reviewed this, I guess, in the context of the Nick tape. But what usually happens, TC is just too low. I mean, you may want to check it out. We can discuss it later. But it's called convoluting mechanism as well now. Basically, it's just RKKY like oscillations. I mean, then you can get pairing because you get negative and positive regions, and then you get pairing. So that's
okay.
But it's just TC is usually just too low. Maybe you may want to check it out.
TC. That's interesting.
Yeah, my sound
that's interesting because
I could not hear any comments, but we'll certainly have time to discuss it later.
Sorry, we talk later. Sorry.
Okay.
Okay, so any more questions, comments? So if not, let's thank the speaker again. Thank you very much, Lauro, and I hope you don't. Is it too cold there?
Right now, I'm not sure, but here usually if it's doing 2 degrees, I'm happy.
If it's what, 2 degrees?
2 degrees, I'm glad. So
okay,
it's not that cold.
It's not that bad. It's not that bad. Yeah.
Yeah.
Okay. Let me see.
I was basically renormalized by Sweden.
Okay, so thank you very much, and we are closing our series of seminars next week. I hope with Andrew Mitchell. So I hope you guys to see you guys next week on Thursday. So thank you very much, and we see each other next week.
All right. See you guys.
Okay. See you guys.
Thank you.
Bye. Thank you.